Okay, in section 5.2, we're going to define something that's called the definite integral. Now, the notation is going to look very similar to what we saw in 4.9 for the indefinite integral. I'm going to be looking at something that looks like this, the integral from a to b of f of x dx. Okay, so the difference is that I'm going to have these numbers here that are going to essentially correspond to the endpoints of my interval. Okay, so we'll have something like, so maybe here's a and here's b, and here's my function f of x. Unlike in section 5.1, I'm not going to be requiring my function to be non-negative anymore. So this is going to mean the signed area. Now, obviously area can't be negative. So signed area is different from area. Signed area is area but with a sign attached to it. So signed area can be negative. It's the signed area between the graph of f of x and the x-axis over the interval from a to b. And for right now, we're going to be supposing that a is the left endpoint of our interval and b is the right endpoint of our interval. We'll eventually see that it's possible to define this if I had a over here and b over here. But for the time being, we're going from left to right here. Okay. All right, so what does this mean? Well, the rule is this. I'm going to draw in walls at a and b, connecting the x-axis and the graph of the function. If I look at the area that's in between there, I've got this area which is above the x-axis and this area here that's below the x-axis. And the rule is we count it as positive if it lies above the x-axis, and we're going to count it as negative if it lies below the x-axis. Okay, now that may seem very strange. That's right now just a definition. I just want to point out that that means sometimes the x-axis is playing its usual role as the floor, but when my function is negative, the x-axis actually becomes the ceiling that we have, and it's the graph of f that's actually equal to the floor. Okay, so why would we do this? Have this thing that we define as signed area? Is it just some weird math thing, or does it actually mean something? Well, I'm going to give you an example. Let's suppose I have a velocity function. So let's suppose I'm putting time here, and we'll say we're measuring that in hours. And let's say we're putting velocity here, and I'm measuring that in miles per hour. Okay. And so maybe we've got something like, so over a 4-hour time period. Let's suppose that my function looks something like this. Over the first hour, the velocity is constant at negative 60. Now, that would mean the speed is 60 miles per hour, but we're going in the negative direction. So velocity is a signed quantity because it indicates the direction as well as the speed. Okay. And then maybe over the next hour, we change things around and our velocity changes. I'm going to have it change in a linear manner so that this is a nice straight line here until we hit positive 60 miles per hour. Okay. Now, realistically, I wouldn't have a sharp corner right here. Realistically, this would be rounded because I know that velocity is a continuous and a differentiable function because the derivative would be the acceleration. I'm just going to sort of exaggerate this and let it be a sharp corner right here. And then let's suppose that for the next 2 hours we went at 60 miles per hour. Okay, so my trick was I went in the negative direction at 60 miles an hour for an hour, and then I started to slow down So I'm still going in the negative direction, but I'm slowing down. And then I turn around at this moment in time here, and I start going in the positive direction until I hit 60 miles an hour, and then I stay at that speed for 2 more hours. Okay. So what I want to do is see if we can't calculate a couple of definite integrals that we have here. If I look at the integral from 0 to 1 of the velocity, now this would be dt because my input variable here is a t rather than an x. I can draw a picture of what that represents. Okay, so this was time 1 here. Okay, so we're talking about finding the area of this rectangle. But I can see that that's going to be negative because we're below the time axis here. Okay, so I've got this, where this is 1. Now, I can either say this is a height of 60, and then just remember that the area is negative, or I could actually mark off, I'm going to view that height as being negative 60. So if I have signed area, the reason it's negative here is because the height is actually something that I'm counting as negative. And so this would give me negative 60 times 1, which is negative 60. And let's see what that represents. If I look at the units, that was miles per hour times hours. Those would cancel. I'm getting negative 60 miles. Now, we saw in section 5.1 that if we integrate speed, this process is called integration. I don't think we used that terminology in 5.1. But if we calculated the area between speed and the time axis, we were calculating a distance. And I warned you that we were insisting that that our velocity be negative, we were insisting that our velocity be positive so that velocity was actually speed. Now I'm allowing velocity to be negative, so I can get a signed area. And what that represents is not the distance that I've traveled, but that's my displacement. So after 1 hour, I ended up 60 miles in the negative direction, we'll say south, from where I started. Okay. So the reason we're going to allow ourselves to have negative signed area is not because we're thinking of this as a geometry problem and suddenly we want to have negative area, but because very often that area is going to be a metaphor for something else. If I have something that I can calculate by multiplying two things together, velocity times time, for example, then I can represent that metaphorically as an area. But a negative velocity that's constant over a period of time is going to give me a negative displacement value. Okay. All right, let's suppose that I wanted to integrate from 0 to 4 the velocity with respect to time. Okay. So I'm going to draw in a wall now at 4. That's at 4. Okay. And now we're looking at all of this area, which will be positive, and this area here, which will be negative, together with that negative 60 that we already had. Okay. Now, what I'm going to do is just drop a perpendicular straight down here. If this was a straight line that was going from negative 60 to positive 60 over this interval of length 1, that's going to cross through the x-axis halfway through. Okay, so I can sort of view this integral that I want to do as a sum of signed areas. I don't have to do it all at once. I can say that's going to be this one, which was negative 60, and then we'll have this one, which will also be negative, and then we'll have this one, which will be positive, and then we'll have this one, which will be positive. So I've got 2 rectangles and 2 triangles. Now, for this triangle, the height here is negative 60. The base would be 1/2. For this triangle, the base would be 1/2. and the height would be positive 60. And for this rectangle, the base is 2, because I've got a 2-hour time period from 2 to 4, and the height is 60. So we're getting negative 60 minus 30 plus 30. I'm sorry, not minus 30 plus 30. Minus 15 plus 15, because the area here would be 1/2 of the base times the height. Base times height is negative 30, half of that is negative 15. Plus 15 plus 120. So the 15 and the negative 15 cancel out. This positive area cancels out that negative area. Negative 60 plus 120 is going to be 60 miles. So if I'm integrating velocity, I'm going to get not distance, which is what I get if I integrate speed, but displacement, which is the difference between where I ended and where I started in this problem. So if I traveled this far in the negative direction and that far in the positive direction, the net result is I traveled 60 miles more in the positive direction, so I've ended up 60 miles in the positive direction from where I started. But that's sort of why we're going to allow ourselves to have signed area, because we really aren't going to be thinking of it as geometric area. We're going to be thinking of that area as a metaphor for something else. And if what I'm integrating is a velocity function, velocity times time is going to give me, if it's a constant velocity, it gives me the displacement. And when it's a changing velocity and I integrate it, that also gives me a displacement.